In this video, we're going to talk about the basic concepts, and this time isomerism. We're going to go through 3 different types, which is we're going to start with chain isomerism, then positional, and then we're going to do this functional group isomerism. And we're going to go through different examples and the definition of structural isomerism as well. So here, as I said, the definition of structural isomerism is the same molecular formula but different structural formula. And we're going to explain what that means as we go through the 3 different examples that we have here. So our first example is going to be chain isomerism, where you introduce branching. We're going to be talking about, in terms of chain, just alkyl chains, so hydrocarbons generally, but they can also have functional groups attached to them, and the chain can just change shape. So if we look, we've got 2 examples. We've got butane, and we've got 2-methylpropane. So if you go along and you count, 1, 2, 3, 4, and then we look on the other one, we can see it's 1, 2, 3, and 4. So it's 4 carbons in each one. You can count that from the name as well. But means 4, and then you've got meth, which is 1, prop, which is 3. So 1 plus 3 is 4. So you can see they've got the same number of carbons. And because they're both alkanes, they will have the same number of hydrogens because they follow the same general formula, which is CnH2n plus 2. So if that's CnH2n plus 2, it's C4H10. So they both have the same molecular formula, but you can see their structures are different. So they're a different structural formula you can see here because of this branching. So they are isomers of each other. And the specific bracket they are, they're a structural isomer, and within structural isomers, we have this type of chain isomerism where you just change the shape of the chain. So I just want to make sure you totally understand that and totally get where it is. So if we look here, we've got butane, and you can see with butane, I've got 4 carbons. Okay, there's your 4 carbons, and I'm putting the 4 bonds like that. Okay, and then I take my other one, and I take 2-methylpropane, and the 2-methylpropane is 3 carbons, and then it's got 1 carbon coming up position number 2. And then all I do is I put the hydrogens in. So as I'm putting the hydrogens in, hopefully you can see from there. Okay, and I put all my hydrogens in. You can count and you can see that it's H10. So 4 there, plus 2 is 10. And then we've got the 3 on there. Okay, and they're just finishing off with the hydrogens. Okay, so all our hydrogens are done. So if you count them all, you can see 3, 3, 3, which is 9, plus 1, 10. So we've got this displayed formula, and we've got this skeletal formula. Now, which one was quicker to draw? Yeah, again, I'll say skeletal formula every time. And what you can do is just rearrange skeletal formula. As long as you have the same number of carbons and it's the same functional group, you can rearrange those branches all around. So all I did is take this carbons right here and then just put it on top. And then it has exactly the same molecular formula and just has a different structural formula. So therefore is a structural isomer. Now, if that's the case, I also want to point out one more thing. And one more thing is look at the boiling points. The boiling points of this is 273, 261. Later on in the future videos, we'll talk about how you can have different boiling points related to the shape of these hydrocarbons. And it's related to how close they can get together. We'll talk about that in a later video, but it's important to realise that the same molecular formula, but they can have different properties. But as I said, these are 2 examples of structural isomers, butane and 2-methylpropane. Our next type of structural isomerism is positional. And this is where you change the position of the functional group on your chain or on a benzene. So we're going to go over chlorobenzene first. And this applies to any functional groups on benzene. You can just simply change the position of the functional groups relative to each other. So we've got here 2 functional groups, both chlorines, and they're at position number 1, 2. Earliest numbering system, really important, 1, 2. We then take that, we move that to 3. And therefore we've got the same molecular formula, different structural formula. So it's a structural isomer. Then we go and move it to position number 4. And again, we've got same molecular formula, different structural formula, because the chlorine is in a different position. Now that's quite simple and applies if you have different functional groups on a benzene. But what if we did it with an alcohol and we combined positional and chain isomers, which essentially you have to do because there's only really one type of isomerism in this video, and that is structural isomerism. We're just breaking it down into chain, positional and functional group, which is next, just to make it so it's easier to understand. But essentially in the exam you're going to get asked how many structural isomers are there. You're not going to get asked how many chain or positional. Now there is a chance though that you might get asked about group, but we'll talk about that in the next section of this video. So let's do the alcohols and let's look at a simple molecular formula. Now the molecular formula is of an alcohol, I've already told you that, but the alcohol molecular formula is CnH2n plus 2O, sometimes written also as CnH2n plus 1OH. Now, here we have, and we're going to give you one which is C4H10O. So there's the one we're going to do, C4H10O. So if you think about that, we know it's an alcohol, because that's how I introduced it, but you would know that through the general formula. So if you knew the general formula, you could work that out. Now, if that's the case, you then go for the simplest alcohol. The simplest alcohol is just to put a straight chain, and there's 4 in a straight chain, and then there is your OH on there. So your OH on there is at position number 1. There's 2, 3, 4 carbons. So if we're going to do that, that's butan 1-ol. Okay, so that's butan 1-ol. We'll then go from there and we draw the chain again. But this time, we put the OH on position number 2. So position number 2 would be there, and that's our positional isomer. Now, if that's our position number 2, we could then move along and we could say, well, what if we put it in position number 3? So position number 3 would be like that, and then you'd put your OH on position number 3, and then we could also put it in position number 4. Okay, position number 4. So that's 1, 2, 3, 4. Now this, and that's 1, 2, 3. This is a big mistake. I'm hoping you're looking at it now and going, why is he doing that big mistake? And that's because if you look at it, the earliest numbering system is what you should be using. So if we look at that, the earliest numbering system is 1, 2. If I get rid of this, okay, and then apply the earliest numbering system to this, you will see that's 1, 2. Well, 1, 2, well that means that is exactly the same as that. And this we would name as butan 2-ol, and we would also name that butan 2-ol. So it's exactly the same. So what we do is we don't need that, we are going to rub that out. Then we're going to move that same idea and move it onto here and say, okay, you think that's butan 4-ol? Well, what if the earliest numbering system, okay, was applied? The earliest numbering system applied would be 1, 2, 3, 4. Okay, so that means that's number 1. Well, that means that's butan 1-ol. Butan 1-ol, we already have butan 1-ol, so basically we don't need that either, and we get rid of that. Okay, right. So we realise then we only have 2 positional isomers, butan 2-ol and butan 1-ol. So we're then going to go and we're going to look at chain isomers, because we've done our positional isomers, and we're going to do the chain isomer of the first one here and see what that looks like. Okay, so they'll go 1, 2, 3, 4. So let's do 3 carbons. Take one of these methyls off to make a chain, and the only place they can put it, I can't put it here, that would turn it back into this long chain. Can't put it here, that would turn it back into this long chain. The only place I can put it is here. And then I keep my OH at exactly the same place. Now if that's the case, and I look here and I go, right, okay, what is this actually named? What was this actually named? So that would be 1, that would be 2. So this would be 2-methyl to start off with. 2-methyl. Okay, and that would be prop, because 3 carbons. Okay, and a propan 1-ol. So propan 1-ol. So that's propan 1-ol. Just finish that up. Okay, so that's propan 1-ol. So at this point you have to think to yourself, have I finished? Have I done? Okay, have I done absolutely everything? Okay, well, once you change your chain, you can then think about whether you can change your position again. So my position is at number 1 for the ol, or maybe if I put it at position number 2. So if I put it in position number 2, let's do it up here. Okay, I can go, there we have it. And then I put my OH at position number 2. A bit longer. There we go. So what I've done then is then change that into OH on 2, methyl is on 2. So it'll be 2-methyl. Okay, and that would be 2-methyl. And then it would be 1, 2, 3, prop. And it's propan 2-ol. So 2-methyl, propan 2-ol. So I just want to go through that from the start to the finish. What we started at is we said, right, okay, what is the simplest alcohol? How can I change the position? Once I've changed the position, how can I change the chain? I changed the chain. Okay, and then I thought, well, now I've changed the chain, perhaps I could change the position again. So I changed the position. So I ended up drawing 4 different isomers of this general formula C4H10O and 4 different alcohols. Our third type of structural isomerism is functional group isomerism. And functional group is in brackets just because sometimes they call it group isomers and they don't call it functional group isomers. So just be aware, group isomers is functional group isomers. Now, functional group isomers, they're just isomers with a different functional group on them. So if we look here, we've got 2 examples. So the 2 examples are propan 1-ol, and both of these have the molecular formula of C3H8O. And you could be expected to draw these out. So if we look at this, we've got 3 carbons. So let's draw the 3 carbons for propan 1-ol. So there's your 3 carbons, and then you've got 8 hydrogens and 1 O. Now it's propan 1-ol, which means it's got an OH. If we count here, remember 4 bonds to a carbon, 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 hydrogens on that one, C3H8O and 1 oxygen. Now the methoxyethane, this is a functional group ether, which is not really, you don't really do it as one of your functional groups on the course, but sometimes they can introduce it in terms of giving you some background knowledge to it so you can use it, or they can use it in this in terms of functional groups. So if we look here, that's an oxygen. Okay, and that oxygen then has an ethane attached to it. 1, 2. Okay, and then it has a methyl on the oxy. Well, essentially they're both on the oxygen, but that is your longest chain, and then this is your shortest. Now, if we look here, we can then count the hydrogens again. 1, 2, 3, 4, 5, 6, 7, 8, and 1 oxygen. So they have the same molecular formula, but you can see different structural formula because they are different functional groups. And that is the first one of the types that we're going to show you in this segment of functional group isomers. So our second type of functional group isomer is alkenes and cycloalkanes. So alkenes and cycloalkanes both have the general formula of CnH2n. So if we look at this, we can draw one. We've got hex-1-ene. Hex-1-ene double bond at position number 1, 2, 3, 4, 5, 6. Okay, so there's a hex-1-ene. If I just take that, these 6 carbons, and I just put them in a ring, and I do that. Okay, this is cyclohexane, this is hex-1-ene. Both of them have the general formula CnH2n, and therefore they're functional group isomers of each other, And that formula is C6, C6, 2N, H12. And again, stop this video, have a look at this type and just say, well, okay, is there the right number of hydrogens? Can you count the hydrogens? You are going to be expected to look at skeletal formula and be able to realise how many hydrogens there are, but I can assure you there are 6 carbons and there are 12 hydrogens on each. Our final type of functional group isomer is aldehydes and ketones. With aldehydes and ketones, we probably haven't done the video on aldehydes yet, so I'm going to introduce what an aldehyde group is. Now, it's written as CHO, and normally has an R group on it as well. So basically all we do is we put the C, and we put the double bond O and the H, and that is written CHO. So if we do propanal, and I'm going to do this one in displayed formula just because we're introducing this aldehyde functional group. Okay, and you've got propanal. So all you're doing is making it 3 carbons long because of the prop. The al is this bit here. So there is your al, and that is propanal. Now, what I'd like you to do, a little activity while you're watching this video, is try and work out what's the general formula of that. So what is the general formula of this? Now, if you count it and you count the hydrogens and things like that, you can say, right, okay, 1, 2, 3. So that would be Cn, and you are expected in your exam to work out some general formulas sometimes. And you get 3 carbons, 1, 2, 3, 4, 5, 6 hydrogens. So that, I think that would probably be CnH2n, and we leave behind an O. There's always going to be one O in our aldehyde, if you have one of them. So if we look at that, and then let's try the next one. So propan-2-one. Now propan-2-one is a ketone. So a ketone, it says RCOR. Now let's explain that a little bit better. Now it's 3 carbons in length because it says prop. Okay, and it says RCO, so that means there's an oxygen on the carbon, and it says there's R groups either side, so there must be carbon groups either side. So those R groups are carbon groups. Now that oxygen is a double bond oxygen, so this is my ketone functional group essentially, and then all I do is fill in all of the hydrogens. And again, 4 bonds to each carbon, that's the only reason I'm doing it. And you can see here, now, stop. Does this fit this general formula? So if you're looking at this general formula, does this structure fit that general formula? Again, stop the video, do it yourself. Don't wait for me to explain, stop the video, do it yourself. So we have Cn, 1, 2, 3. Okay, hydrogens, 1, 2, 3, 4, 5, 6, 2n. Well, C3H6 is CnH2n, and then 1O. So basically what we're saying is, yes, both of these, their general formula, CnH2NO, and they are both functional group isomers of each other, and they're ones to look out for on these type of questions. But there's one last thing I want to say about all of these functional group isomers. The most prevalent one I've seen is the cycloalkane and alkenes one. So even though these can happen, and they may happen, you still need to know them, and the alcohols and the ethers may happen, you still need to know them. The most prevalent one, the one I've seen the most of, is cycloalkanes and alkenes. So it's really good to give yourself some practice on those. And what I recommend that you do is you just basically take any aldehyde, try and draw a ketone, which is going to be an isomer of that aldehyde. Try any alkene, and try and make it into a cycloalkane, and try and take any alcohol and change it into some form of ether. And you can do that easily as practice, so you can get really good at doing functional group isomers.